Starting from tomorrow, I will do the following, as usual. I will discuss with each of you personally things about your kind of education, what you know, and also interests, and in trying to understand what you are going to do in the future. So usually what I'm doing, I'm inviting, say, 2 people at once to my office and just discuss things. Right? Also to want to understand how well you feel my course, and so what are your recommendations, to say in this way. So the plan of today's lecture is the following. We will discuss Fermi theory, of weak interactions. The theory which describes, in particular, beta decays. Then I will introduce some important notions which we are using in particle physics, namely cross-sections, and we will compute or estimate cross-section of neutrino interactions, and also number of events, in different experiments. And this you will need to make exercises, to perform exercises, which I will probably give either tomorrow or after, or on Thursday. And finally, we will start to discuss discovery of neutrino. Let me remind that we finished last lecture by a hypothesis of Pauli, which explains paradoxes of beta decay, and in particular bismuth 216, which decays into polonium 216 plus electron. And Pauli suggested to add another particle. Let me put anti-neutrino, because that time people haven't discussed neutrinos or anti-neutrino, the difference, but I will use our modern notations for particles. And more precisely, I can say that this is electron neutrino, which we have established later. So there were 2 paradoxes. One is that the spectrum of electrons was continuous. It's not just fixed by difference of masses of 2 nuclei. And this is explained because the energy release in this decay actually is shared by electron and neutrino. And so individually, electron energy and neutrino energy are not fixed, but what is fixed is the sum, just according to energy conservation. And so the energy of electron can be essentially kinetic energy, or total energy can be from total energy from mass of the electron up to Q, energy release. So it can be in this interval. The second paradox is relation between spin and statistics, but essentially what people at that time kind of established, that there is a conservation of statistics. In initial state, it is Bose statistics. In final state, without electron, without neutrino, that would be Fermi statistic, because the spin in final state is semi-integer. Adding neutrino, particle with the spin 1/2, resolve this paradox. Neutrino as 1/2, resolve this paradox, because the total spin in final state is also integer. Electron has a spin 1/2, and therefore there is no problem with spin and statistics. Now the theory of weak interactions and beta decay, the first one has been developed by Fermi. In 1934. And Fermi implemented or included in his theory two things. One is discovery of neutron. And after discovery of a neutron, the nuclei theory has been developed, according to which the nuclei are the states, composite states of protons and neutrons. That was the result also the paradox related again to the spin, because before people thought that electrons are inside the nuclei, and instead of neutron before, what has been considered as the state of proton and electron, but then it was problem with the spin. Okay? So, according to Fermi, the beta decay is nothing but transition of neutron inside the nuclei to the proton. So this is beta decay. One of the neutrons, which is sitting inside the nuclei, transforms to the proton. Second point, which is implemented into Fermi theory, is hypothesis of existence of neutrino, so Pauli hypothesis. The key point that in construction of theory of beta decay, Fermi used analogy. He used analogy with electrodynamics. In my course, I will not discuss electrodynamics because you have some special course, but I think you have already some knowledge of this, and of course Fermi had some knowledge of electrodynamics by that time, and he used this to construct his theory. So analogy with electrodynamics. And let me underline that analogy is extremely heuristic, important heuristic principle in particle physics, I think in physics in general. And what we are using when we are trying to construct a theory or understand something, in the first place we start to use analogy, trying already to use what we learned before and see how we can implement this, what we learned before, to the new situation. So what is interesting that actually nature likes repetitions, and you can see many analogous things even in different energy levels and for different systems. So it looks like this is not just an empty attempt, so there is something behind this. Nature, again, likes to repeat the same relation, the same properties for different systems. So it is not so stupid to try first to use some analogy. So let me just mark this again, and remember, when you will do something and try to develop it first, you may try to use some analogy. So analogy is important heuristic principle. And let me say that, again, what I'm saying, that nature likes repetitions. So, what Fermi used? Let me recall first some elements of electrodynamics or electromagnetic interactions. So the simplest is the interaction of electrons with photons, right? So you can have scattering of electrons on nuclei due to exchange of photon. So it could be emission of photons by electrons, and electrons can scatter on electrons due to electromagnetic interactions. I don't know how far you managed with Giovanni, but tell me if something is not clear. I will go into details. So the electromagnetic interaction of electrons, for instance, can be depicted in this way. We have electron, which emits or absorbs photon and change energy of momentum. So this is so-called Feynman diagram, simplest one. And usually we are kind of showing by these full lines fermions, by these vector bosons or gauge bosons. Here we have vertex, and in the case of electromagnetic interactions, this is electric charge of particle. I think for time being, this is enough to understand. So that's kind of remembering that we have interaction of electron with photon in this way. So photon also interacts with protons. You can write the similar diagram for proton and for all other particles. Now, the Hamiltonian, or Lagrangian if you want, which describes, and Hamiltonian and Lagrangian, at least for interactions, just have opposite signs, can be written in the following way. It's coupling constant, then wave function, or in quantum theory this is operator, of the electron in final state, then gamma matrix, then wave function of electron in initial state, and then the field or wave function which describes photon. Mu is Lorentz index. Mu is 0, 1, 2, 3. So tell me if it is known for you or not. Not yet. So you haven't yet studied. But that essentially corresponds to such a diagram. So this is a so-called Dirac conjugation. Do you know what is Dirac conjugation? Okay, good. And that describes actually the production of particle or simultaneously absorption of antiparticle. Because in the second quantization, let me ask, have you passed second quantization? Not yet. Have you studied second quantization?
We will start this week, I think, with that.
Okay. Oh, yeah, you should, yeah. So it's just a matter of maybe a week or so when you will learn everything. So, is this clear? This is how we describe in the field theory the interaction. And of course, here is a coupling. Okay? So this is a wave function which describes produced electron. This is absorbed. And this is what corresponds to photon, or the electromagnetic field. Now you need to write these terms for all particles which have electric charges, because they all have electromagnetic interactions. And now, using these as kind of fundamental element of the theory, you can build up all possible processes. For instance, electron-electron scattering, so you can scatter electrons, and they will exchange photon, and that will be depicted in such a way. So you have electron, which is transformed into electron, and here you have electron and electron. And here you have exchange of gamma. So this is second order process because we have two interaction points here and there. So you can write the same diagram for scattering of electrons on proton. Okay. So ask me a question because I will use a little bit this. Yeah.
Usually, There some of the directions is the time direction.
Yeah, usually this is the time direction. Yeah, writing this, yeah. Yeah, so that's time direction. And there are final rules which actually allow you to write, say, amplitude. So using this fundamental Hamiltonian, you can compute or write the amplitude of the process. And then compute probability of the process, which is moduli squared of amplitude, like in quantum mechanics. And then there are so-called Feynman rules, which actually immediately tell us what we should write, which corresponds to this line, that one, and that. And here we should write propagator of a photon. Who knows what is a propagator of photon? Yeah, somebody knows? No, not yet. Or green function, if you want. Okay, so again, for time being, for us, it will be enough. That what was known. That was maybe not in such a form, because Feynman produced his theory later, much later than before after Fermi. But again, so I'm using more kind of modern language. So these are elements of electrodynamics. So here, let me say again, this is coupling constant. So the bigger the coupling, of course, the more intensive interactions are, the bigger amplitude, the bigger cross sections are. Okay? So this, what is called current. So this structure, when you have wave function or operator of absorbed particle, this is emitted one, and this is gamma mu, and so this is 4 vector at large, 4 vector. This is what is called current, 4 current. Actually, if you use if you kind of make transition to non-relativistic case, that is precisely will reproduce usual current on classical way, because 4 components will be reduced to density of particle and density times velocity. So going to classical case, that is reduced to this 4 vector, which gives you the density, and here is the flux essentially. So there's 4 components here. So this is why we call current. So this is the current, right? Because here we have velocity and then number density, and of course if you add the charge, you will have really current.
In non-relativistic case, you would write E, J mu, A mu in that case.
A, so say again, what?
Like J, this is J mu that we know in electromagnetism, right? The current which is not relativistic.
So this is general, so no, this is for non-relativistic, and then yes, we can write with interaction with photon. Here is vector potential, right? Or vector field. According to electrodynamics, and this what Fermi used, what we have is the following. You may have the process when electron is flying in the electromagnetic field, right? Suppose you have nuclei here, and there is a field produced by the nuclei. This photon accelerates or changes the direction and can emit gamma, again, can emit photon. So this is the process of emission of photon in the electromagnetic field. So this is the process. So what is important that the photon was not in the initial state. It was produced. It was not existing before the interactions. It is not like a composite. You had some composite electron which then splits into electron and photon. So it was produced in the interactions. Now let's come back to beta decay. And the problem was, yeah.
At the level of this diagram, what's our the conservation laws that we like try to don't violate, like conservation of charge,
Yes.
spatial momentum.
Yes, so of course everything, so we have electric charge conservation because we have electron in initial state, and electron in final state. Then you need, you can apply energy momentum conservation for final particle, so that total energy, so sum of the energies in initial state equals sum of the energies in final state of your products. Yeah, so we are applying energy momentum conservation for particles in initial and final state. Total energy in initial state should be equal to total energy in final state, and the same for momentum.
Okay. So in that case, we have an energy coming from the field.
Yes,
Right.
so that's why I have written. I cannot write the process like this, just emission, right? Then I will not satisfy energy momentum conservation. And the part of the momentum is transferred to the field and energy. Yeah. Right. Now, how we would describe the process of beta decay? Remember, according to Fermi, this is transition of one of the neutrons inside the nuclei into proton. So we have neutron in initial state, which is then transformed to the proton, and somehow electron and electron antineutrino are emitted. So this is beta decay of neutron. Okay? The question was that how you can contain electron and antineutrino, especially inside the nuclei. So people still thought that the particles which we are observing in a final state somehow were contained inside the nuclei. And the point is that this neutrino is very weakly interacting. So Paul introduced this as a neutral particle. The question was how this particle is kept inside the nuclei. And that's what Fermi was saying, that in analogy, with electrodynamics, the pair of electron and electron antineutrino were not in the initial state, but they are produced by neutron. So the process is like this. We have neutron, proton, and here electron and antineutrino. Precisely in the same way as proton can produce gamma. So the analogy is but Fermi is saying that instead of gamma in electromagnetic interactions, I have the pair of electron and antineutrino. Therefore, instead of electromagnetic field, I will have the following object. I have here index mu because I want to have covariance or Lorentz invariance eventually, right? So I need to have something which contains this gamma mu. And so Fermi said, okay, we need to substitute this photonic field in the Hamiltonian by the current which contains electron and neutrino. So therefore the Hamiltonian, which describes weak interactions of beta decay, should be written in the following way. They have proton. And what I will do for simplicity, I will not write, and sorry, I should say already this, instead of writing this psi everywhere, I will just write as E, and it will not produce any confusion. You will see just instead of operators or the fields, I will write the particles themselves, notation of the particles. Okay? So you need to treat this as the field of electron. Here is the field of neutrino, or wave function of electron, wave function of neutrino. So then the Hamiltonian should be written in the following way: P gamma mu. Again, so Fermi said, okay, in analogy with electromagnetic interactions, we probably can try that weak interactions are also organized somehow, made of currents. So we have this current, which actually describes for me transition of a neutron to proton. And then instead of photon, I have another current, E gamma mu and neutrino. And I need to put some coupling here, which is called Fermi coupling. And usually it is introduced in such a way, square root of 2. So G Fermi square root of 2. Plus Hermitian conjugate. So I have to have conjugate. Questions? So important point which I haven't stressed, when we discussed Lagrangian of Hamiltonian of electromagnetic interactions, let me write it again. What I had is, say, electron, I can write for proton. Proton, gamma mu, proton, E, and here is electromagnetic field. But all these wave functions are taken in the same space-time point. So, and what is this? This is density, actually. We are saying this Hamiltonian about density of H. So this is energy density of the interaction. See it in this way. All the fields here are taken at the same point, and this is again reflected by this our diagram. When interactions of electron with photon occurs in the same space-time point. Eventually we are doing integration, of course, over space-time point when we compute amplitudes. So, what Fermi did, he said also, okay, all these fields should be taken in the same space-time point. So let me put here x, 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 x. So this is density of Hamiltonian. So what is the meaning of Hamiltonian? This is operator of energy, right? In quantum theory, in quantum mechanics. This is the density of Hamiltonian, which means that energy in the unit of volume. So then what is the unit of H? What is dimension of H? Tell me.
Energy for.
Yeah, well, you know already. So good. So it's all mass to the 4 power. So this is the energy over centimeter cube, say, right? So, and remember, we can measure the distances in inverse energy units, and therefore the dimension of density of the Hamiltonian is this mass to the 4 or energy to the 4th power. Yeah?
They're also at the same moment, right? We talk about the same space-time points.
Yeah, so that's, yeah. So let's put here x.
So
which means that this is energy density in a given space-time point. Yeah?
when we write the Hamiltonian or Lagrangian for any given diagram,
Mm-hmm.
we look at one vertex and we somehow multiply all the edges that is connected.
No, you see, okay, maybe this will clarify. When I was, so if you have just one vertex, yeah, so this is a single space-time point, but then eventually when we compute observables, we need to make integration over space-time. Now, remember I had this diagram with two vertices. Then this is, each vertex corresponds to its own parameter space. So it's x and here's y.
Different points in space.
Different points, yeah. So if it is second order process. So this is what is called local interactions when we have the same space-time point.
And can we interpret AU as the wave function of photon in a quantum mechanical sense?
Yeah. This is precisely, yes, this is wave function, yeah. Well, at quantum level, this is operator, which means that, and the field theory, in quantum field theories, you know, this is operator, which can be represented as the sum over operators of production and annihilation of photons with different momenta, and then in front of that you will you are putting the corresponding wave function. But again, so I don't want to go out to this because you will study this in length. So what is important for us that in analogy to electromagnetic interactions, Fermi introduced this type of the Hamiltonian. I will say Hamiltonian, but you also always means when it is written that this is density of the Hamiltonian. In the same space-time point. So that was Fermi has introduced. Well, actually, let me say that this is the simplest Hamiltonian which you can write. Suppose you not even use analogy with electromagnetic interaction, as Fermi actually did, but just knowing that you want to describe this process, what you need to have a presence of all four particles in your Hamiltonian, right? So, which means that somehow you need to write the product of four fields or four components which corresponds to the process. The simplest way, if you take them in the same space-time point. So this is just on the principle of simplicity, you can write this. The only subtle point is it is not clear if you should put gamma mu here and gamma mu here. Of course, you may write even without any gamma, right? If you just want to. So gamma came from this analogy. And actually Fermi was wrong. And I will tell you. And in principle, it could be that some contributions come from interactions without gamma mu. So you may actually write different Lorentz structures. You can write here without gamma mu. You can write this gamma phi, and here gamma phi, this is pseudoscalar. You can write these tensor interactions, like this sigma mu, and here is sigma mu. I don't know if you know what is this. What is this? Okay, you can write this axial vector. It's gamma mu gamma phi. Here is gamma mu gamma phi, or something like this. So this is more general. But this is the simplest. So this is with analogy, and at least you see immediately that all four fields should be present because they are interacting in one point, and it should be, say, overlap of these wave functions of these fields, right? If you want, you can look at this in the same space-time point for a process to proceed. Okay. Now let us look in more details on properties of this Hamiltonian. So that's our theory. So properties. So the Hamiltonian is Lorentz invariant. Right? We have here gamma mu, and here is gamma mu, and this is Lorentz invariant structure. What is interesting that nowadays people are discussing breaking of Lorentz invariance, although we haven't seen no one process, no one effect of this breaking. But it is kind of active area of research now to look for possible effects of Lorentz violation. Okay, so keep this somewhere in mind. Maybe some of you will work on this eventually. Second, this Hamiltonian has the structure current times current. So this is product of two currents. Hamiltonian can be rewritten then as G Fermi square root of 2, and then here we have a hadronic current multiplied by a leptonic current, where what we call hadrons are strongly interacting particles. I'm kind of making this announcement in advance. So this is what we call hadronic current, which is gamma mu n, and this is leptonic current, Gl mu, which is E gamma mu neutrino. Product of two currents. So using analogy to with electromagnetic interactions, Fermi has written really vector currents. It's vector currents. So it's gamma mu. Structure with gamma mu is called vector current. You can actually introduce pseudo vector, which is defined as gamma mu times gamma phi, and this is what is called pseudo vector or axial vector. Let me put here axial vector, and this produces vector structure. What actually was realized later is that Fermi was wrong. And in fact, here in the weak interactions, what operates is a combination, gamma mu, vector current, and axial vector current. So this is 1 minus gamma phi. So that's a correct structure instead of gamma mu, but that was established much, much later. What is interesting that you can actually detect or observe this additional element. If you use polarized nuclei, then that becomes metal. But since in the initial studies, people use unpolarized objects, so that was not important, and therefore Fermi could predict very precisely and describe very precisely heat decay.
Is this a symmetry violation?
This is a parity violation. That's what actually corresponds to parity violation. This one parity violation has been discovered, then people were forced to introduce axial vector current.
I have a question.
Sure.
We discussed that usually the Hamiltonian density in the other class, that it's not Lorentz invariant, but it transforms as the energy, as the zero component of an energy tensor.
No, so it's kind of okay. So that's
It's not in.
so this is Lorentz invariant structure, right?
Yeah, I've seen now this, but like now, no, maybe we have to. I have to ask.
Why don't we use Lagrangians instead of?
Well, you can use Lagrangian, absolutely. So that was kind of used, and then Lagrangian of interaction is minus Hamiltonian of interaction. Remember, the Lagrangian was introduced kinetic term minus potential energy. So that corresponds to potential energy, energy of interaction. And of course, you need total Lagrangian would contain this part which describes free propagation.
But this part is still Lorentz is running.
Yeah. Now, what's next? Let me put here. The next important feature is that the currents which we are introducing here are charge current. Yes. In the case of electromagnetic interactions, the currents are neutral in the sense that electron go to electron, emitting photon. So proton go to proton. There is no charge of the fermion, right? There is no charge. So the current, and the current was like this in the magnetic interactions, and this quantum object has zero charge, right? The Q is zero, because suppose this is charge -1, but this here we have conjugate, which is +1. So this operator has charge 0. In contrast, in the case of weak interactions, we have charge currents. So the object like E, gamma, mu, neutrino, has the charge +1. Okay? This one has -1, and therefore energy is conserved. So electric charge is conserved because here is proton with conjugate, it has minus charge. So in the case of weak interactions, we have charge currents, the product of charge currents, not neutral current, at least in this case. So later we will discuss that also neutral currents have been discovered. But they are responsible for different processes. Next one, let's see what is dimension of coupling F in this case. In the case of electromagnetic interactions, the coupling, at least in our units, was dimensionless, it's E. Now, so what is dimension of GF? If someone can tell. So what is dimension of?
10 to the 4
Why?
because of the wave.
So let's see. H is energy density. It has meaning of energy density, which means that this is mass to the 4. Right? So what is dimension of fermionic field? No. So we can come back and to see what is Lagrangian or Hamiltonian of free propagation of electron. It contains mass and then psi, right? So I think you heard this already.
Yeah.
Right? So, which means that this is mass to the 4, which means that should have mass to the 3rd power, right? Or each of them, so dimension of psi is the mass in the power of 3/2. Right? So here we have 4 fermions, and therefore all this structure has dimension mass to the what? 6th power. Right? Each of these fields, fermionic fields, has dimension mass to the 3/2. And then you have 4, and therefore total dimension is 6. And therefore, to match dimensions, we need to conclude that this guy has dimension 1 over the mass squared. Okay? This is actually a very important conclusion because that may actually testify for, and I will discuss a little bit later, that this interaction in fact is not local. And these two currents should be taken into different space-time points, and there is exchange of some particle between these two currents. So, but before this, let me say how this GF has been determined. Knowing this Hamiltonian and knowing the rules, you can compute what is decay rate of neutron or nuclei, and this decay rate should be proportional to GF squared, right? Because what we are doing when we are computing the amplitude, we first compute matrix elements. So we take this Hamiltonian and then compute a matrix element between initial and final states, right? So initial state was just neutron, and the final state is proton, electron, and antineutrino. So we need to compute this element, and then the probability of decay, or the rate of decay, is given by moduli squared. So this is constant. It just went out of this moduli square, and so we conclude that rate should be proportional to G Fermi squared. Okay? So Fermi made the computations. He computed what is the rate, and then he just compared with what has been observed. And in this way, because everything else is known, so the only unknown is this GF, and then you can compute your probability. Then from observations of experimental rate, you can find what is this GF. And numerically, GF can be written as 10 to the minus 5. And here, mass of the proton. You can easily remember this. Quite good accuracy. Numerically, it can be parameterized in this way. It doesn't mean that you have proton exchange. It's just since you know what is the mass of the proton, you can write this in such a way. So mass of the proton is approximately 1 GeV, which means that this G Fermi is 10 to the minus 5 GeV minus 2. Yeah, GeV minus 2. And finally, again, the fact that we have this coupling constant, which has dimension, testifies, and in fact, Fermi already kept this in mind, that probably this is similar to what we have in the case of scattering of electrons. In the case of the scattering of the electrons, on the electrons. So that's the process. And it can also be written as the product of two currents. So it's E gamma mu E. Here is again E. And here what I will write here, gamma mu E, and here's G mu. So that's a propagator of photon. This is something which is responsible for the proton. So in the second order, electromagnetic interactions also look like this, but you need also to add here a propagator of photon, something which describes this photon which is exchanged. So Fermi thought that maybe these are interactions of not of this type, and they were called as four fermionic interactions. For fermionic interaction. So Fermi thought that maybe it's not like here all fields are interacting in the same space-time point, but maybe again in analogy with electromagnetic interactions, you have something like that, like this. So that you have here neutron, here you have proton, and here you have electron, and here is neutrino, and so it's antineutrino then. It is emitted. So that actually this current should be taken in two different space-time points, and then you need to have some mediator between point X and point Y. So, and this is propagator of this mediator. So here we should put here index mu, this index nu, and this is mu nu, X minus Y. And so this object is so-called intermediate boson, which actually mediate these interactions. In contrast to electromagnetic interactions, this vector boson should be massive and heavy enough. Electromagnetic interactions are long-range interactions, and therefore we can resolve points where you have interactions of two different currents. Now, experimentally, everything is okay with such a structure without any mediation. This means that the particle which is kind of exchange or mediates this interaction should be heavy enough. And the point is, if the particle is heavy enough, then it can propagate only some short distance. It's virtual particle, and it actually propagates distance which is inverse of its mass. I will discuss this later because we will discuss the introduction of vector particles. Just saying in advance, the truth can be like this, but because the mass of W is much bigger than energy release in the process, this interaction is reduced to this one. And actually, this propagator is reduced to 1 over the mass of this W boson squared. And this actually explains the dimension of this coupling constant. Questions? Well, actually, Fermi even went further. He said, okay, maybe these couplings are also like electromagnetic coupling constants. And then you can estimate what should be the mass of W boson to explain the observed value of G Fermi. And what he has found that mass of the W boson should be 30 GeVs, 30 times bigger than the mass of the proton. He was almost right, but not quite, because actually the couplings here are not electromagnetic coupling constants. And therefore, the mass of the W boson is different. And this we will discuss later. So the mass is 80 GeVs. Bottom line is, for low energies, for the energies which are smaller, much smaller than the mass of the W boson, you are not resolving this. So you cannot see with this microscope of this energy resolution this distance. So that looks for you as just one point. Maybe I should say this. Let me say this. It's kind of again similarity with what we have in optics. So when you want to see some small structures, and it's actually the same story as we had in the first lecture when we tested point-like character. So if you want to see small structures, you need to irradiate it in your microscope by waves with very small wavelengths. Right? Because if you have big wavelengths and you want to explore very small structure, you will not see the structure. You need to have the wavelengths which is smaller than the size of the object you want to explore. This is like a microscope, right? The same story. I mean, the same physics. It's important. It's the same physics. If you understand in one place, then it's easy to understand in another places. So, in our example, when we consider the processes with this energy release or energy of colliding particles, this means that we probe our system. with wavelengths, which is 1 over p, it's 1 over q. If q is small enough, then lambda is big. And if q is much smaller than mw, and this distance is inversely of mw boson. So that's typically the distance between x and y is 1 over the mass of the W boson. And therefore, you do not resolve this. You do not see, your experiment is not sensitive to this structure. You just see this as a point-like object. I will repeat these arguments later when we will discuss introduction of W boson explicitly. So which means that at low energies, you can use just this Hamiltonian and don't worry much on what is behind this G Fermi. Of course, you can compute still some corrections, which are very small, which are proportional to, say, Q square over W boson mass squared, if you want to some next order corrections. Yeah?
Is it correct to say that the low energy, where the electromagnetic force and the weak force have the same mathematical Hamiltonian structure, so are we considering them to be the same force, or?
Well, they are not, so the point is inverse, I would say, because at low energies, weak interactions look like here, like a point line. At high energy, and electromagnetic interactions are look as exchange of photon. We can see the different points. At high energies, these interactions really become very similar. And this is actually the basis of construction of the standard model, which is joint, which is unified theory of weak and electromagnetic interactions.
Yeah. But I mean, the starting point should be that they are like have the same mathematical structure of
Why? You know, this is the result of experiment. So what I want to again underline, so I'm trying to show you how these things really develop. So that Fermi constructed because he knew about beta decay. He didn't start it from some mathematical principles. Okay, so please remember how things were developed and how they were constructed. So it was this beta decay. That was the starting point. He used analogy, but he didn't sort, well, to some extent, he used the same mathematical kind of structures, right? He used these currents, and he used vector currents, and at this point, he already used some similar mathematical, if you want, formalism in these two. But you see, that eventually even Fermi was not correct because this structure is not correct because, you know, it should be gamma mu minus gamma mu gamma 5. This should be not just coupling constant, it should be propagator of W boson and things like that. More questions?
Maybe according to these pictures, it seems like the propagation, for example, that process, the photon propagates instantaneously, like it happens at the same time. It goes from one point to another point 0 time, but it's not like that.
So you need eventually to do integration over space and time, and it actually occurs, of course, the intensity of this exchange is different. So if two electrons are at very big distances, you can even neglect it. Say, I can start with some asymptotic states when I can completely even neglect this gap. Then two electrons approach, and then, yeah, you have then exchange, right? And so when they approach, then the intensity becomes bigger and bigger.
there is a photon traveling between the lights, well, that's the
Yeah, yeah.
picture we should take.
Well, this is virtual actually. In this case, it is virtual.
Okay.
It's not on the mass shell. The Q square is here is not zero when we have this type of exchange. You can compute what is transfer momentum. You can compute if you have this process. You can compute what is this form momentum of this of gamma, and it is not zero. You can find because you have here. If you change momentum here, then for photon Q square is not the mass of the photon, which is zero. So, actually, it's even negative. I don't know if you have this knowledge of virtual particles. Have you?
No.
Not yet.
I have
Not
heard
yet.
that,
So,
I-
which are not on the mass shell. So, which means that when you have exchange of these particles, then so energy square minus p square is not the mass of the particle, right? This is not what we are saying on the mass shell. And but of course, these particles cannot exist long time, so they should exist during the time and in space-time, which is inversely proportional to this Q. So they are emitted, but they should be absorbed by a particle itself or by another particle.
Can we observe that?
What?
The virtual intermediate particle.
Well, we can extract properties knowing what we are observing here, electron.
But if you want to see.
But how you will see photon? Again, you see photon by interactions.
Not for photon, but for W boson.
Virtual. You want to see virtual W boson.
This boson that the intermediate.
Yeah,
Virtual one.
but you can also produce a boson, W boson on mass shell. What we are saying. Yes.
And when we do the experiment.
So, for instance, you can do this by annihilation. So, like at CERN, it is produced copiously. You may have U quark and D quark, and they annihilate and produce W boson on mass shell. But again, it's also, this is very quickly decaying particle, and because of this, you have very big energy uncertainty in any case. Right? So, but with accuracy, say 2 GeVs, you can say that yeah, this boson is on mass shell.
So when someone predicts the mass of this W boson, the experiment to test if it has that mass is like that one. Not
Yeah. So what you are doing is actually, if you want, yeah, you can see this is real, because then this W boson may decay. Maybe this is not the best. So, excuse me. Then this W boson can decay into electron and neutrino, and then you can measure invariant mass. But again, this is we are in this. I will discuss this in detail. And so you can measure what is effective mass of W boson. Sorry. Да. Ты что, ладишь на лекции сейчас? Sorry. So more questions? Again, you can observe W boson, you can measure its mass and establish what it is. And actually it appears as a resonance. When particles have very quick decay, it shows up as a resonance in, say, final products. Okay. So Fermi introduced this Hamiltonian, which actually describes quite well beta decay. So he could manage to compute the amplitude and the probability, and so he can predicted, let me say, predictions are or consequences. From this, using Hamiltonian, he can find what is the energy spectrum of electrons. And it was in very good agreement with what has been observed. So that was really a success. This continuous spectrum, which Chadwick has measured, was well reproduced by the theory, which is really a success. By the way, if it would be not a local theory, not just point-like as here, the spectrum would be different. So this is one of the confirmations that really, if there are some mediators, they should be quite massive. Second, this Hamiltonian allows to predict some new processes. And one of them is inverse beta decay. So, do you know what is algebra of reactions? Okay. Beta decay, let me write it here, is when n go to p plus electron plus antineutrino. Then what you can do, you can move one of these particles to initial state by changing particle to antiparticle, and that process should exist also. So here, what we can have also, using this algebra, that an antineutrino can interact with, so what we do, we are having a neutrino here, and it can go to, let me see, it will go to electron plus a neutron. Let me put electric charges correctly. That should be plus, that should be like this. Right? So I put a proton on, so I put electron to this side, here antineutrino, and this is neutron. As I look at this, you may get the same reaction, this reaction. Another important process, which follows from this Hamiltonian, is electron capture. Electron plus proton go to neutron plus neutrino. So these processes have been predicted, eventually observed. Okay?
Did people know about these processes before Fermi introduced this?
I don't think so, because that comes from this Lagrangian Hamiltonian. And they have been discovered later, so this one has been observed, say, 20 years later, after Fermi constructed this theory.
So the probabilities to having different combinations are not the same.
They are not the same, you need to compute it. Well, in some cases they are quite similar, because here we suggest a single reaction decay, right? So the strengths of this can be similar if you have the same, say, energies of electron here, or energies of the particle. For high energies, they are quite close. They should be close, the same.
I'm asking this because maybe to have a decay is more easier than to construct things.
Well, I don't know in which sense it's easy. Of course, if you have just neutrons, you have usual matter, and you have neutrons, nothing to do. Here you need to create the beam of neutrinos. From practical point of view, they are different. So that might be easy, because this is what happens inside the nuclei, because what happens is you have atomic nuclei, and then in various cases, electron can be captured by nuclei. So again, nothing to do, just take correct nuclei and wait what's going on. Right?
I thought was maybe some entropy is going up if we have some decay. Maybe
Yes.
it's more often to see it in the nature.
Well, I don't know how to compare these things. Actually, your argument about entropy is correct, because if something can decay, it will decay, right? So that you transfer some potential energy into kinetic energy. So if you have neutron, and neutron has certain mass, so that's potential energy, right? Neutron can decay in this way. So in the final state, you will have a proton, electron, and neutrino, and they have kinetic energy, so they're moving. So that, in a sense, you increase entropy in a system. This is why, actually, again, this statement: if something can decay, decay. If something is not decaying, then this means there are good reasons for some conservation laws or something like that. By the way, this is very good lesson how to develop the theory. And now we are doing also the same thing. So now we are in a position that we have standard model. And people are using so-called effective theory, some beyond the standard model, following these Fermi arguments to a large extent. Because you can look at this in the following way. These particles were known. Of course, neutrinos were not known, but so that's at low energies. It is known. And writing like this, we are parameterizing some new physics, and this new physics is W boson. So actually, what is behind this exchange of W bosons, which is new physics in comparison with this low energy stuff. Now the story appears to some extent, because we have standard models, some particles say below 1 TeV scale, and we can imagine that there's some new physics at very high scales with very big masses. It's just repetition of the same story. And then we can parameterize this new physics by writing Lorentz invariant and standard model symmetry invariant operators, similarly to what is done here, thus parameterizing some new physics which you don't know yet. Well, this is lateral remark. I don't know if you can ask, or we can do more detailed discussion, have more detailed discussion later. So with this, of course, the question was how to discover neutrino, what to do, how to convince that neutrinos really existing object. And then, you know, the kind of the attitude was the following: people didn't like to introduce new particles, as I was saying. And in fact, by that time, only a few particles were known: electron, proton, neutron, dot. So what else? Nothing.
Yeah. We said we can introduce this actual current in that term.
Yeah.
It has the same coupling constant, or is different?
Sorry, which two? We can
The actual current.
actually.
Yes.
Well, that's a good question. It turns out that this is the same coupling at quark level. At the level of proton and neutron, it is not the same.
So
But
that's
very
why
cool.
it's lower. We cannot see in the beta decay because it's lower energies.
No, we can actually we can measure this coupling, right? So we measure this coupling.
But
right?
for the actual current,
Yeah, we measured eventually even this for axial current, and I will discuss this. Yeah. So that was measured. Again, this is experimental fact. So a priori, we didn't know what should be there. Now, you see, the point is the following, and actually, so the similar arguments they repeat after many years again and again. Question, what is this? Okay, beta decay, fine. But maybe still there is no neutrinos, but some new dynamics is involved. Really, one needs to discover neutrino to claim that this is a real particle. So how to establish that neutrino is not some phantom or something like some effective non-conservation of energy or something like this, some new dynamics or so. To discover, to establish that neutrino is a real particle, one needs to satisfy the following criteria. One needs to convince yourself that this is something which propagates. So this is property of real particle. It's not like some dynamics of decay, but you need to establish that you really produce something which propagates between, say, two different space-time points, x and y. So it is produced in point x and then interacts in point y. And it can transfer momentum and energy. And it transferred quantum numbers. Like lepton number or spin, right? So then you are convinced that although you do not see neutrinos, but if you find that here is beta decay, okay, and here in some other point there is an interaction, and you put the energy to this point and some transfer to this point quantum numbers, then you are convinced that neutrino is a real particle. So what was suggested already in the early days, that you can have to use inverse beta decay to detect neutrinos. So you have the point x where neutrinos are produced, this source, and you have n, p plus electron plus antineutrino. Well, it can be neutron, but it can be a nuclei. So usually we are using nuclei, not a free nucleon. So then neutrinos propagate, and in the detector we can use inverse beta decay, nu e plus proton, go to positron and neutron. So beta and piles made first computations of cross-section of this process of inverse beta decay. I think it was 36, 37. And what they have found, and actually that will be one of your exercises, that one needs to have enormous amount of matter to see this one interaction. So for a given neutrino, the probability that it interacts with probability 1, you need to have something like 1 astronomical unit of water. It's a huge one to, you see, to observe at least one event. So that the probability is of absorption is 1. So at that time, it was thought that practically impossible to detect neutrinos, to observe that. Before we will discuss how still it became possible, I want to introduce some notions which we will need to our consideration. Questions? And I first want to introduce cross-section. And then we will compute cross-section for neutrinos, and then we will make estimations of the matter, amount of matter needed for neutrino to be absorbed. Suppose we have neutrino which enters our detector medium with number density of particles n. So this is our usual setup. Suppose the length is L, and then the probability for neutrino to detect, to interact or to be absorbed in our detector is proportional to n. That's clear. The more dense detector you have, the more events you expect, right? It is proportional to L, the size of your detector, and some characteristic of interaction, how intensively neutrino interacts with the scatterers or with particles of our medium. This is what we call cross-section. The unit of sigma can be extracted from this expression. So P is probability, which is dimensionless. This is 1 over centimeter cube. L is centimeters. And therefore sigma should be centimeters squared. This formula works provided that P is much smaller than 1, and this is what usually satisfied for neutrinos. Otherwise, you need to make integration. So if the cross-section is big enough, then you need to make integration over dx and from 0 to L. If you have big probability that neutrino can rescatter again. But this is not the case for neutrinos, so I will use the simplified formula. So why is cross-section? What is the physical meaning of this? And what is the sigma? At classical kind of level, you can write sigma as area occupied by scatter multiplied by opacity. So we can look at the scatter as some area with some transparency or opacity, and so your particle is coming, and if it hits this area, it is interacting. So that would correspond to the formula which you have written here. And this is because if you take unit of area, then neutrino which enters this area will see scatterers. Then the probability of interaction will be given by area occupied by scatterers divided by area itself, total area. So the probability, roughly speaking, is given by this area occupied by scatterers, and also one needs to multiply here by transparency, so opacity, multiply it by opacity. So what is the area occupied by scatters? It's sigma, and then the number of scatters is given by n, density, multiplied by L. So this is number of scatterers, right? And in this way, we are reproducing the formula which is written above. Okay? So classical level is that you have a scatter, so your neutrino is coming. And if this is unit, this is 1 centimeter. And it's 1 centimeter, right? So unit of area. And this is reflected into n. So then n multiplied by L is nothing but the number of scatterers inside this unit area and the length L. This gives some feeling what is the sigma, why we call this cross-section. This is characteristic of interaction. So this we need to compute to find the probability of the process, or probability of interaction. Okay? And we will compute the probability of neutrino interactions with protons tomorrow. Ask questions. So sigma is characteristic of the strengths of interaction with individual scatters. And so this is essentially number of scatters in the unit of, in this type of the volume, where we have this unit of area and the length L. Yeah.
We said that neutrino and electron pair is produced after as a final state of this interaction.
Mm-hmm.
When some particles are produced, do they always come in particle and antiparticle pairs? Like in this case, sometimes we denote this neutrino with antineutrino in that process.
So let me write for just what we are eventually considering is electron antineutrino plus proton go to a neutron plus electron. So that's what we are. Now ask your question.
No, I'm questioning this for the neutron decay, where we argued that they are not, they were not in the nucleus, but they were produced. How can we actually say that they are produced, that they are not in the nucleus?
You mean this n? Let's go.
Yes,
This is proton plus mu e plus e. Okay, first, what are the forces? The first question is what are the forces which actually keep neutrino in the first place? So, what kept neutrinos inside the nucleus of neutron? It's very weakly interacting. Even this model for neutron, when we have proton and electron, okay, there are forces. But then we have the problem with the spin. Okay, because proton and neutron have spin integer, and the neutron has semi-integer spin. This neutrino is okay, but there is no forces. So if you introduce some forces which could keep neutrino inside, then you could easily detect neutrinos. There is no electromagnetic interactions. Now, if you introduce some new interactions for neutrinos, again, they should be strong enough to keep it in neutron, inside the neutron.
I'm asking this because when we try to produce a new particle, like in electromagnetic case, I think we just produce photons that may lead to produce a proton and antiproton, for example. Like if you want to produce a new massive particle, or
So, and the photon is emitted by what?
emitted by, for example, an electron that deflects.
Okay, so you want to have the following process. You want to have electron, and electron should still interact with something, right? So let's try to build up the diagram. Okay. So what electron is? If it's just free electron, it cannot produce, right? So that then, but you can probably introduce some interactions. So you want to have pair production of. So the only what is it is electron, then you have you may have the following process. Okay, you may have E plus, E minus annihilation, or things like that. And the final state you have proton and antiproton. Yes, you may have this.
Yes. For example, this process or any process, any other process, if you want to produce some other particle other than photon, we always produce one photon, which leads to pair production of new other particles, right? We cannot just produce proton after some process.
Well, you need to see what are kind of couplings or what type of the interactions particles have first. So what I should compare is, tell me what you want to have. You want to have immediately without photon, right? So what?
Without photon, is it possible?
You have E plus, E minus, and say proton and proton. Without photon, it is possible. When you have here mediator Z boson, you may have such a diagram. But again, maybe there are some contact interactions. A priori, we don't know. We know that they are strongly restricted. Again, a priori, it is possible that such a vertex exists without any mediator. However, there's a very strong bound on the coupling here. We know that all the observables till now are in agreement when you have this production via exchange of photon or Z0 boson. You may have higher order processes. And this is because we know what are couplings of electrons. We know all the couplings of electrons in the standard model. Of course, it could be that some new couplings exist. That is not excluded, but we have strong bounds on these couplings. We also know what are the couplings of protons. We know that this exists. So we can construct these processes. Observations are in agreement with this. Now, that's question mark. If it exists, but it should have very small strengths, much smaller than this one. We haven't seen the traces of these contact interactions. Yes, people are introducing kind of contact interactions, but this is speculation, so they are not observed.
But in the end, in practice, if those mediated production mediated by bosons is more common one, if that is more common one, in the end we see always pair productions of new particles. For example, in our case we produced a neutron electron, or in this case...
No, you may have more particles, but that will be kind of... so, for instance, here you may have the process like, say, Z0 and then another E plus, E minus.
But all the productions comes in pairs of particles.
Because we have the couplings of this type in pairs. So elementary couplings, but you can build up more complicated interactions via exchange of these particles. Now, in neutron decay, there are 3 particles in final state, right? So you have 1 particle in the lowest state. Number of photons can be emitted quite big, but those are elementary particles. This is what we know. So this is our standard model, which tells us. Again, it is not excluded that some more complicated interactions exist in principle, but they are not observed yet. or maybe never will be observed. Okay? Okay, so oops.